Welcome back to Digital Learning. In the Design of Steel Structure course, we have already completed the design of purlin. Now we move on to the load calculation of roof truss. In this video, I am presenting the load calculation procedure on roof truss. Generally, roof truss is subjected to three types of loads: dead load, live load, and wind load. In the calculation of dead load, the dead loads are contributed by three components. One is roof covering material, including all services and fixtures, self-weight of purlin, and self-weight of roof truss. So, first I explain the dead load calculation on roof truss. First, I will consider the self-weight contributed by the roof covering material. In this calculation, I consider the unit weight of roof covering material, including the service and fixture loads. Then I multiply with the corresponding tributary area, where 4 is nothing but spacing between the truss, and this 9.693 is nothing but the length of top chord on one side. I have windward direction as well as leeward direction. So put together, I get the total load coming from the roof covering material is 18.998 kilonewton. Coming to the weight of the purlin, we have completed the design of purlin, by which I know what is the size of the purlin for this roof truss. It is nothing but ISLC 100, whose weight is nothing but 7.9 kg per meter run. Here I am converting into Newton, then it is kilonewton. The unit weight is given in terms of kg per meter run. Therefore, I am multiplying with the length of one purlin. I'll get the weight of one purlin. Here in this roof truss, I have 14 purlin. Therefore, the total weight of purlin on one intermediate truss is nothing but 4.34 kilonewton. This 14 comes from, I am explaining the 14 number from this diagram. So see here, this is the truss we are working in this particular module, where I'm taking fin fan type truss, in which the purlin, the node points are nothing but 14. So along this 14, so these are the position I'm planning to place the purlin point. Therefore, I have 14 points over which I am placing the purlin. Therefore, I have 14 purlin in this calculation. That way, I get the weight of the purlin. Then coming to the weight of roof truss, there is an empirical equation to calculate the weight of the purlin, which is nothing but this expression, in which you have to supply the plan area of one truss distribution area, that is the spacing of the truss into span of the truss. If you put these values in this expression, you will get what is the weight of roof truss in kilonewton per meter square. Again, it is a plan area. I am putting again the plan area of the truss in this expression. I'll get what is the self weight of the roof truss. By adding the weight of the roof covering, weight of purlin, and weight of roof truss, I'll get the total weight on the roof truss on any one intermediate roof truss is this much. I'm rounding up to 30 kilonewton. This 30 kilonewton has to be distributed along these node points. So where by seeing the structure, when I'm counting the intermediate points are nothing but I have 5 intermediate point. Here again 5 intermediate point. Totally I have 10 intermediate point. When I am taking here there is a half distribution area. I am taking 11th point. Then here this is half, this is half. Therefore, I'll take the total load to be distributed along 12 nodes. Therefore, I'm dividing this total load, that is round off to 30 kilonewton divided by 12. This is nothing but number of node points. This 30 kilonewton has to be distributed uniformly. Therefore, any one intermediate node subject to a maximum dead load of 2.5 kilonewton. So, but when I want to calculate the load on any one in end node point, it is nothing but this load, that is the load expected on any one intermediate nodal point divided by 2, I'll get n node point loads. But when I'm coming to this ridge point, here I'm adding this half the load and the half the load and make it as one load at this ridge point. This is about the distribution of dead load on the roof truss. Coming to the live load calculation of the truss. Already we have calculated live load on the purlin as 0.514 kilonewton per meter squared. This load is not to be taken directly on the roof truss. So according to IS 875 part 2, we know that the live load on the roof truss is nothing but 2/3 of the load on the purlin, which is nothing but 0.514 kilonewton per meter squared. Therefore, here the live load on the truss is nothing but 0.343 kilonewton per meter squared. So already we know that this area is a plan area. Therefore, I'm multiplying with the plan area. I'll get the total load on the total live load on the truss. So as I have explained earlier, the number of node is 12. Therefore, I'm dividing the total load by 12. I'll get the load on any intermediate node point. Similarly, at the end node point, I have half of this value, which is equal to 1.03. This is nothing but live load calculation on roof truss. Coming to the wind load, in the previous lectures, we have an idea that what is the wind intensity on the windward direction of your roof truss, that is this side, and what is the intensity on the leeward direction of your roof truss. Considering your direction of wind is in this direction, I'm considering this is my windward direction and this is my leeward direction. The wind intensity is nothing but 1.67 kilonewton per meter square, which is already we have calculated in our previous lectures. And the intensity on the leeward side is 1.57 kilonewton per meter square. When I am multiplying the corresponding projected area, that is, this is the length of the slope length of the top chord into the spacing of the truss. If I multiply the intensity, I'll get the total load. There are 6 node points on one side, say. So here, this is a half node, this is a full node, 1, 2, 3, 4, 5. This is half, this is half. So I'm putting 6 node points on the windward direction. Similarly, 6 node points on the leeward direction. So therefore, I'm calculating what is the load intensity on any one intermediate node point, which is equal to 1/6 of this value. Therefore, I am getting 10.79 kilonewton. For at the end node, I'll get only half of this value. Similarly, on the leeward direction, I'll take the corresponding intensity, but the same projectile area, and divided by 1.6, I'll get what is the load on any one intermediate point on the leeward direction. Similarly, this is on the end node on the leeward direction is nothing but 4.88 kilonewton. Now I am showing the loading diagram of the dead load and live load. See here, this is my truss under consideration. I have mentioned all the loads are in kilonewton. See here, only at the n nodes I have 1.25, rest of them are intermediate nodes. Similarly, I have marked the same as on the roof truss, that is the live load on the roof truss, that is 2.06 will be the intermediate load values of live load and 1.03 on the n load. But here I have half becomes one node at the ridge point. This is suitable for dead and live loads. Coming to the wind load, I know that the wind is always normal to the roofing sheet plane, but your dead load and live loads are always in a gravity direction. Since it is acting in the perpendicular to the roofing sheet, so I have 5 intermediate node and 1 intermediate node. So accordingly, I take the loads on the windward direction as well as the leeward direction. Once you know the dead load, live load and wind load, calculate the member force on these members and you tabulate like this. So don't feel that this is very complex. Here I have marked the number of members in the truss is nothing but 35 members, but there is no need to worry about it. When I am considering the dead load and live load, here the trusses seems to be symmetrical with respect to geometry as well as the loading. Therefore, you can use the symmetry of the truss. So you can able to calculate the member force on any one side which will be similar to on the other side. But when I coming to the wind load, you have to calculate the member force in all the members and you list all your member forces. Here you have to take the combination of dead load and live load, multiply the partial safety factor for different members which is listed in this particular truss. Similarly, you calculate 1.5 times dead load and wind load here, from which you have to take the design load. In the next class, I will explain how to calculate design load for your member design calculation. So anybody you are aware of StatPro, you can also do the analysis by StatPro. Don't worry about it. I prefer or I recommend to the students to use method of section to analyze this member forces. That is member force due to dead load, live load and wind load, and take the combination and calculate the member forces. Design member force is nothing but what is the maximum force on the top chord, that is from 1 to 12, take the maximum force in the top chord. That will be the design force for the top chord. We should have same section for the top chord. Similarly, take the bottom chord, that is 13 to 17. Take the member force, the maximum member force for the design of this bottom chord. Similarly, the tie member, here there are certain tie members are longer in dimension and subjected to tension. Similarly, this is said to be major slings and this is nothing but minor slings, and these are nothing but struts. This is nothing but major strut and this is nothing but minor strut. So don't worry about it. These are all said to be web members. You please check this is to be taken as one couple of member, and also you can include this. Rest of the member, this fan members are to be on same size. So when you do the member design of roof truss, you can have a single sections. Single section, that means one form of section for the top chord, maybe different cross section for the bottom chord, or otherwise use the same section if it is preferable, or say for the tension force in the bottom chord. Then you place same member for this two members, that is member 25, 26 and 27 and 28, as well as 21 and 32. But rest of the fan members could be of same size. So this is the way you have to do the design force. That means you take the maximum force which is in the top chord, that is your design force for the top chord. What is the maximum force in the bottom chord? That is the design force for the bottom chord. What is the design force for these members? That is the maximum force I am mentioning. Similarly, what is the maximum force in these fan members? Take that force as your design force for the design of member. Thereby, you will get one type of cross section for the total top chord, one type of cross section for total bottom chord, and one form of cross section for this members, and one form of cross section for the fan members. So this is all about your load calculation of roof truss and the analysis. So thank you very much. If there is any queries, you please share your comment in your TCE courses. Thank you very much.